Hi, welcome back to ECE484. This is our last lecture of fall 2021. Before we get started, just a couple of comments about the final. In terms of the logistics, it's going to be very similar to the midterms, except you'll have a longer period of time to write the exam. In terms of the content, it will mostly focus on the material since term test 2, although you can expect a minority of the questions to be about the pre-midterm material. And maybe some of the multiple choice questions to be some based on pre-term test material, so earlier material in the course. In terms of studying, go back, make sure you do the term tests again, do the problem sets again, maybe do exercises from the notes. Plus there's lots of material and there's textbook references in the course outline if you want to do textbook questions. Okay. All right, so that's all I'll say about that. Let's finish the course. All right, so where were we last time? So we've been doing control design for discretized system or discrete system. And we were trying to solve the issue that normally you do not have sensors for all of the state variables. And so we wanted to design this observer, which is another dynamical system, which reads the inputs to the plant as well as the outputs of the plant, takes that information and uses it to generate an estimate of the state, which we called x hat. Okay? And this was the structure of the observer that we justified last time, right? So it depends on some of the plant parameters, but then also there's this L term that shows up, which we get to design, right? So when it comes to an observer, at least for this structure, designing an observer means picking an L matrix, which is, you can think of it as a gain, as we saw last time, okay? And what we saw is basically was that the estimate will converge to the plant state if and only if you design L so that the matrix A plus LC is stable, i.e. has all of its eigenvalues with magnitude less than 1. Okay? And what we saw last time was that designing this L to make A plus LC stable is very much like the way you would design a state feedback to stabilize a system. Okay? Okay, so that's what we talked about last time. And then we're just going to introduce a little bit of terminology that really is nothing new, but just so that we're on the same page in terms of terminology. We will call the pair CA observable if the transposed versions of them, so A transpose, C transpose, that pair is controllable, okay? And this is consistent with what we saw last time, right? If this guy is controllable, then you can place the eigenvalues of A plus LC anywhere you want, okay? And if you want to test for observability, well, very simple. Find the controllability matrix of A transpose, C transpose, then take the transpose of that matrix, and you will get what we will call W sub O for observability, and that is the observability matrix. Okay? And again, it's just the transpose of the controllability matrix of A transpose, C transpose. And so in terms of tests, we have that CA is observable if and only if the observability matrix has rank n. Okay? Also for terminology, we will call the pair detectable if their transposed version is stabilizable. Okay, so it's just a kind of a terminology that we use for observers. And so if we wanted to test for detectability, we use the same test we used for stabilizability, except we transpose it, right? So we'll say that CA is detectable if and only if this PBH test has rank n. Again, that's just the transpose of what we saw last week for every unstable eigenvalue of A. Okay, so that's just some terminology. And so let's just summarize this section before we do the last one. So we have the following summary. The observer, given by this one, so it's the same observer we had above, asymptotically estimates the state of this plant for any initial conditions, this is what we saw last time, if and only if you can design L so that A plus LC is stable. This is what we saw last time. Okay? And then, in terms of designing that L, what do we know? The eigenvalues of A plus LC can be assigned arbitrarily by suitable choice of L, is equivalent to saying the pair is observable, which is again equivalent to saying that this observability matrix has rank n. By the way, MATLAB can generate this observability matrix for you with that command, which is equivalent to saying that the PBH test holds for every single eigenvalue of A. Okay? Furthermore, you can actually design L so that A plus LC is stable, right? Maybe you can't arbitrarily assign the eigenvalues of A plus LC, but you can at least stabilize, make that matrix stable so that your observer works, if and only if the pair is detectable, and if and only if the PBH tests pass for the unstable eigenvalues of A. Okay, so that's a summary of observability and observers of what we've done so far. And so what we want to do now is we want to do what I said before. We're going to take our observer, our state estimate, and we're going to use it as if it were the actual state of the plant to design controllers. This is our last topic. Observer-based controllers. Okay, so we have a plant. Okay, we will assume that the plant is such that AB is stabilizable and CA is detectable. Okay, so as we've seen, that means that there exists a state feedback which stabilizes the dynamical system. That's stabilizability. And furthermore, there exists an observer so that we can estimate the plant state, and that's the detectability assumption. Okay, so that's the setup. And what we will do, we will design a two-stage controller. Okay, first an observer will generate an estimate of the state. Estimate of the plant state. Then use the state estimate as though it were the real state. In a state feedback. Okay, so that's the set. That's what we're going to do here. Okay, and so the design procedure is very straightforward. We will choose F so that A plus BF is stable. Okay, and we saw how to do that in section 9.1. Then we will choose L so that A plus LC is stable, in other words, for the observer design. And again, we saw in an example last class how to do that. And consider the controller. Okay, so again, it's just going to be the observer with the estimate going through the state feedback. So I'll just write it out, but that's all I'm writing here. So there's the same observer that we had from before, but now we're going to use the state estimate as though it were the actual state to generate our control signal. Okay, so this is an observer-based controller. And if we want to, let's draw a little picture here so that we have an idea of what's going on. So again, in general, what we'll have is our continuous process. I'm going to write it this way. Okay, so this is our hold, our sample, our plant, right? So this is our continuous time process we're trying to control. Okay, and our observer-based controller, let's just copy this. We'll go down here. Sorry, there's like some sort of tractor or something outside. Okay, so let me write it this way. Okay, and so there will, this estimator will generate our state estimate, and it will measure, or that state estimate will then be sent to our gain. F. And that will generate U. Okay. The plant will generate Y. Okay, and the observer will measure U and Y. Okay, so this is our observer-based controller. So the first stage, again, generate an estimate. That's this guy here. And then use that estimate, x hat, as though it were the real state in our state feedback. Okay, you can simplify this diagram a bit, of course, because, of course, the control signal U is sitting on the computer, so we have access to it. So let's simplify a little bit. We can simplify the diagram by plugging in U equal to Fx hat into the observer equation. Okay, so I'm going to replace the U that shows up here with F times X hat and then redraw the system. Okay, and so what it would look like is, again, we'll have our plant. Right, so this is our discretized version of the plant above. And then down here, our observer-based controller, which will look like so. So again, all I've done is I've replaced, in the diagram above, I plugged in the expression for U equal to F times X hat into the observer equation, and now our diagram is quite simple. Okay, so the observer reads Y and produces U, the observer-based controller. Okay, so okay, that seems simple enough, intuitive, right? Estimate the state, then use the estimate. Does it work? Will this actually solve our output stabilization problem? The question now is, does this work? i.e., do we have internal stability? Right, so remember what we wanted is that we want a controller which measures y, produces u, which has the property that when all the exogenous signals are off, and in this case I haven't drawn any exogenous signals, no matter how you initialize the plant, no matter how you initialize your controller, things should come to rest at the origin. Okay? We saw this in chapter 6. We saw it at the start of this section when we were introducing the problem. Okay? So we just have to check that this controller actually results in internal stability. Intuitively, it seems like it should, right? If the state feedback works and the estimator works, you combine them, it should work, but we have to be careful, right? That's not always true. So let's see. So to answer this question, let's take the closed loop state to be the plant state and the estimation error. Okay, so here's the argument. We want to show that no matter how I initialize the plant and the controller, so the plant state, controller state, they should go to 0 because there are no exogenous signals in this diagram. Okay? But it's convenient, instead of looking at x and x hat, to look at x and the estimation error e. Okay? Hopefully you agree that if x and e go to 0 for any initial condition, that implies that x and x hat go to 0 for any initial condition. Because of course, if x goes to 0, then x goes to 0. And if e goes to 0, then you have that, it must be that negative x hat is going to 0. Okay? Okay. So we're going to look at x and e just because it makes it easier. Okay, so we already know how the estimation error evolves. We saw this in section 9.22. So from section 9.22, we know that the estimation error evolves in this way. All right? We saw this is how we came up with the idea of our observer, or the justification that our observer worked. Okay, so we already know how that works. We just need a difference equation for x. Also, we know that this is how the plant evolves. This equals ax plus bf x hat. Okay, but I don't want the x hat in there. Remember, I want to use my closed loop state to be the plant state x and the estimation error e. So I'm going to try to write x hat in terms of x and e. And of course, that's straightforward to do, right? It's just rearranging the equation above. We have that x hat is equal to x minus e. Okay, so now we've expressed it in terms of the state variables x and e. And so we get okay, so in other words, our closed loop state x and e evolve according to the following. Okay, this is our closed loop system. Right? I'm just rewriting the x plus equation and the e plus equation in matrix form. Okay, so we want to, for internal stability, we need that this system here be asymptotically stable. In other words, we need that all of the eigenvalues of this matrix have magnitude less than 1. Let's call this ACL for closed loop. Okay, so in other words, as usual for internal stability, we need that ACL be stable. And that would mean that no matter how you initialize the plant, no matter how you initialize the controller, things come to rest. Okay, but observe, ACL is block triangular. Okay, and so the eigenvalues of ACL are going to be the eigenvalues of the diagonal blocks. In other words, it'll be the eigenvalue of this guy combined with the eigenvalues of this guy. So let's write that down. Since ACL is block triangular, what do we have? We have that the eigenvalues of ACL are going to be equal to the union of the eigenvalues of the diagonal matrices. And so it's going to be the eigenvalues of A plus BF union the eigenvalues of A plus LC, which we designed, right? We designed F so that A plus BF was stable. We designed L so that A plus LC is stable. In other words, by design, the eigenvalues of this matrix all have magnitude less than 1. By the way, this is sometimes called the separation principle. Because it basically says that your closed loop eigenvalues are the union of the two, the design for the observer and the design for the state feedback. And it's called separation because you can design the observer separately. So on its own, you design the observer, then you design the feedback, and the two designs don't interfere, right? They basically together combine to produce the overall eigenvalues of your closed loop system. Okay, and that's it. That's what we wanted to show. This controller actually works. So this implies that for every, so I'm just going to basically write out what I've already said in words, but this implies that for every initial condition of the plant and initial estimation error, we get that x of k, e of k go to 0. Because again, F was designed so that A plus BF was stable, L was designed so that A plus LC was stable. Okay? Therefore, for every initial condition of the plant and every initial condition of the controller, we get that those guys go to 0, and we have internal stability. In particular, we've solved the output stabilization problem. Okay, with a controller, of the form, or with a controller. I'm writing this because when we introduced the problem, we talked about a controller with matrices AC, BC, CC, and DC. So in this case, our controller, the AC of our controller, is given A plus BF plus LC plus LDF. BC is negative L. CC is F, and DC is 0. Okay? So that's our controller. Now, this block diagram that we looked at here doesn't look like our unity feedback, right? We can introduce the exogenous signals. So what I want to do is I want to introduce some of the exogenous signals that you would normally have in your standard block diagram, but not change the controller. So how would this look like if you were implementing it in a unity feedback system? You'd have the following. So let's reintroduce. The reference and the disturbance. In our usual unity feedback. configuration. Okay, and maybe I can just copy it from the notes. Let's see. Here we go. So I called Z the state of the plant, but let's call it, or the controller, but let's call it X hat to be consistent with what we've said in lectures. Okay, so it's exactly the same as what we had before, but notice that the BC matrix changed signs because when the reference is 0, it should be negative times negative Ly. So the reason that that negative changed signs is because in a unity feedback configuration, we have this negative feedback coming here. Okay, so keep that in mind. It's a small change of the sign of L, but otherwise it's the same controller that we've designed all along. Okay, so that's it for in terms of course material. Let's do an example and then we'll call it a day. So I'm going to do a little bit more of a more involved example than what's in the notes. So let's do hopefully a little bit more interesting. So we'll do a kind of a funny robotics problem. So we're going to consider what's called a simplified model of what's typically called Pendubot. Okay, and I say it's simplified because you're going to draw a picture in a second. We're going to say that it has massless links and mass concentrated. At the distal end of the links. Okay, let me draw it and then we'll see what I'm talking about here. So the picture will be the following. We've got a motor at the base, and then we have these two links. It's like a double pendulum, you can think of it as. So link 1, oops, with mass 1 at the end, and then link 2 with mass 2. So let's label things. So let's call this mass 1, mass 2, link 1, link 2, gravity. And what makes this an interesting control problem is that we're going to say that it's going to be an underactuated mechanical system, right? So it says mechanical system has 2 degrees of freedom. Let's call those degrees of freedom, let's give them some coordinates. Let's call this theta 1. Call this theta 2. So it has 2 degrees of freedom, right? There's 2 angles that I need to describe its position. But it's only going to have 1 input. So it's an underactuated mechanical system. And the only input will be the torque that the motor exerts at the base. Okay, so we'll call this the torque. Okay, and we want to design a controller to keep it upright. But the only sensors we have are going to be encoders that measure the angles theta 1 and theta 2. Okay, so let's put some numbers into it and then we'll solve it. We'll design a controller. So we're going to take M1 equal to 1, M2 equal to 1, L1. So everything equal to 1, just for to simplify things. I mean, the procedure would be the same if the numbers were different. Okay, tau is an applied torque. At base. And like I said, optical encoders. Measure theta 1 and theta 2, right? So those are the sensors that we have. We don't have full state sensors, right? We're not going to be able to measure the velocities, but we can measure the positions. Okay, and we want to design a controller Operating with sample period to equal to 0.01 seconds to keep the Pendubot upright. I mean, hopefully you can agree that if we were to linearize this Pendubot at the upright position, it's going to be a nonlinear system. If we linearize it at the upright position, that linear model will not be stable in open loop, right? So we're going to have to do something to stabilize the pendulum at the upright position, okay? And we're going to design an observer-based controller for it. Okay, so this guy's nonlinear. The modeling of it is of peripheral interest, but to be complete, I'll tell you it. So it's a nonlinear model. If we take Q to be equal to the positions of the robot, theta 1 and theta 2, then the model is of the familiar Euler-Lagrange equation. Okay, so fine, that's just one way to write these Euler-Lagrange equations. But I'll fill in with the details of what they are. So that's the nonlinear model. In this case, because of the simplifications we've made, the D matrix is pretty simple. C matrix is also quite simple. And let's see. This is all of peripheral interest, but for you to just verify the calculations later. Okay, so this is a nonlinear model of our simplified Pendubot. Okay. In order to design an observer to keep it upright, we're going to want to linearize it, right? So we're going to try to use some of the tools from earlier in the course. So we're going to linearize this model at an equilibrium configuration corresponding to the upright position. Okay, so you can go and you can generate a state space model, you can find the equilibrium configuration, and then you can linearize about that equilibrium configuration. It's clear though, I mean, hopefully by now you've seen the pendulum before, that at the upright position we're going to want, if you look at our coordinates, theta 2 should equal 0 so that it's upright. Theta 1 should equal 0, so the thetas will equal 0. Their velocities will also equal 0. And we don't need to apply any torque at that point. It'll be 0 torque. So our equilibrium configuration is just going to be theta 1 equals 0, theta 2 equals 0, theta 1 dot equals 0, theta 2 dot equals 0, and tau equal to 0. So we're going to linearize about that equilibrium. Okay, so to be formal though, we would say that our state vector, let's say, mechanical system, we typically take positions and velocities. So I'm going to take theta 1, theta 2, theta 1 dot, theta 2 dot. Okay. The input is going to be the tau, and the output is going to be the things that we can measure. And so in this case, we said we had encoders, so the output is going to be theta 1, theta 2. Okay. Again, you can write down a big nonlinear state space equation. I'm not going to bother doing that. It's just, you can play around with it. I'll post some simulations if you want to see what it looks like, though. Okay, the equilibrium configuration. X bar U bar is, as I said before, all the positions and velocities 0 and 0 applied torque. Okay, you take the nonlinear model, you linearize it, you get the linearized model. I'll write it down so that we have the full equation. Okay, the output is already linear, right? It's the first two state variables, so we don't expect this to be too interesting. Okay, turns out that if you do all your calculations, this is what you get for your A matrix. G. Okay, and then your B matrix for the state space model. Okay, and so again, the idea is now we're going to design a digital controller to stabilize this linearization for this Pendubot. And so what we expect, if we do it carefully, we do it correctly, if we initialize this Pendubot kind of near the upright position, it should stabilize there. Okay, and we're going to do an observer-based controller. Okay, and so for simplicity, take G equal to 10 meters per second squared. Okay, so the numbers are relatively nice in our matrix. Okay, and I'll leave it at that. Okay, step one, if we wanted to do this design. First, we're going to discretize this plant, right? We have our linear model here, piece A, B, C, D, discretize. Plant using the step invariant transformation. Okay, this is a big system, 4 states. I'm not going to do it by hand. I would use MATLAB here. And if you do that, you get some discretized system. I'm not going to write down the matrices because I'll show them to you later in MATLAB, but they're of peripheral interest. Okay, and I'm dropping the delta. Okay, so we took our system and we've got this A, B, C, D. Okay, and I'll show you them later, but it's not so interesting. We're going to design a controller now to stabilize our system. So we should check that AB is stabilizable and CA is detectable. I leave that to you. But first I'm going to design F so that A plus BF is stable. Okay. So we could do pole placement, right? Place the eigenvalues. In this case, it's just an example, so I'm going to use be a bit fancier, but of course you're not responsible for this. But in this example, I'll use an optimal control technique. In this example, I'll use an idea. Okay, this is just to make things simple, right? So basically the idea here in the optimal control is you choose your control, your gain F here, optimal in some sense. Okay, I'm going to show you the MATLAB command I'll use. Discrete linear quadratic regulator And then you have to give it 2 extra matrices. In this case, I'll take Q equal to identity, R equal to 1. Okay, this is just for the purpose of this example to give you an idea of there's more out there. Of course, for this course, I wouldn't ask you to do this. You would design F by finding the determinant of Zi minus A minus BF and choosing F so that you have desired eigenvalues. This is just another way you can do it. And if you do that, I get the following F matrix. Okay, so F would be the state feedback. There are 4 states in our model, so it looks like this. And you can check that the eigenvalues of A plus BF are the following. Okay, they're all less than 1 in magnitude, so we've designed F so that it's stable. Do the same thing with L. Okay. I'm going to again use the same idea, optimal control, but of course you could also do it using the pole placement ideas. Okay. The issue here is that L, because we have 2 outputs, right? We're measuring theta 1 and theta 2. L is going to be a bigger matrix. There are more gains to choose. So again, I'll use optimal control. So same Q and R from above. So remember that you design L as if it were an F, and then you take the transpose at the end. Okay, and if you do this, you will get the following matrix. Okay, so bear with me while I write it down. The numbers themselves aren't so interesting, but what's interesting here, again, it's that L has 2 columns because there are 2 outputs that our system is processing, right? So I said one of the advantages of state space is that you can deal with multiple input, multiple output systems in very much the same way as you deal with single input, single output systems. So in this example, we have 2 outputs, the 2 encoders, and so our gain matrix L for the observer ends up having 2 columns. Okay, you can check that the eigenvalues of A plus LC are stable. So okay, so we did it. We've designed it L so that A is plus LC is stable. Okay, and our controller in this case, there is no D matrix in our plant, so our system is simplified. And this is our final controller. Okay, so of course that's a more complicated example than you would get on an exam, but you get the idea that these tools that we've learned can be used to solve pretty complicated problems. All right, so let's do a simulation quickly. Oh yeah, that's not good. Okay, I will post this on Learn, but okay. The first part is just calculating the model. It's not so interesting. Linearizing. Okay, so let's stop here. We'll discretize the plant. Okay, so just so that you see, there's our discretized A matrix. There's our discretized B matrix. Our discretized C, of course, is the same as the continuous time C, and D is 0. Okay, so I didn't write those down in the lecture because I would argue there's of limited interest. Okay, let's continue to say here. Okay, so our controller, remember I said there was the F that I wrote down in class. There's my observer gain matrix. There's the state space model of my controller. Okay, so has 4 states because we're estimating 4 states. It has a single output because, of course, there's a single input system, the plant. Okay, and if you want it in terms of transfer functions, right, it's going to have 2 transfer functions, right, from each measured output to the control signal U. Okay, okay, so now we continue. So now I'm going to simulate it, and I'm going to simulate it using Simulink. I'm going to pick a random initial condition for the position of the Pendubot and a random initial condition for the velocity of the Pendubot. Okay? Remember that we're working based on a linearization, so this controller should work as long as we start relatively near the equilibrium configuration. And so hopefully I do actually get something close to the equilibrium configuration. Oh, that's not a good sign. So it looks like my initial condition was too far away. Let's run it again. There we go. Okay, so this is not too interesting. What we are seeing is exactly what I said, right? Theta 1 and theta 2 going to 0. Okay, let me actually show you, though, the Simulink diagram. Pretty simple. Here I have the nonlinear. So I'm simulating on the nonlinear model, and here's our controller. Okay, so let's go. Okay, so this is, again, not so interesting. This is just a block which implements those nonlinear dynamics I mentioned. Here's our controller. For some reason, there we go. There's our controller. Again, I've got the biases because I'm doing based on linearization, right? So in this case, Y bar and U bar are 0, so it makes no difference. But remember, when you're designing a controller based on linearization, you always have to have this operating point showing up, these biases. Okay, so that's the setup, simple simulation environment. And so let's actually see this thing move. Okay, so this is the initial configuration. There's some non-zero initial velocity. And so our controller is going to stabilize it upright. So let's watch what that looks like. So the time is slowed down a little bit, but you get the idea. And it's stable. Now, of course, if I come and I tap it a little bit, it should stay there, but you kind of get the idea. Okay, that's really all I had to say. So let's stop there. So that's the end of the course. Hopefully you learned a few things. In terms of following up from this, if you're interested in control, I would highly recommend taking ECE484 in the winter, taught by Professor Dan Davison, who is an excellent professor. I would say the best instructor in the EC department. And there you would learn about more about state space control design. Okay, so it would be building on what we did at the end of this course. Of course, there are robotics courses which use ideas from this, what we've seen in this course. Automated driving courses, automated vehicles, which will use in part some of the ideas we've seen in this course. Yeah. Okay, so that's it. I will see you guys around. I'll be in touch, obviously, on Piazza and so on. And good luck on your exams. I'll stick around if there are any questions.